Today we're going to look at friction. Now, friction is present in many everyday examples. The simplest probably being a block of some description that is resting on the floor, and you apply a force to it and it slides along the floor. Now, we're all familiar with that concept. There is definitely a force resisting the motion, which we know well to be friction. So if we zoom in and have a look at the base of that block, and we look at the surface of the floor on which it's rubbing, microscopically there will most definitely be some sort of a roughness to those surfaces, and that is the predominant reason why there is resistance to motion. Okay, so that would be called surface roughness. There are of course other reasons why there would also be resistance to motion, and those could be molecular adhesion, the fact that the materials are sticky to the touch, and if the materials are slightly soft in nature, they could actually be deforming, and this could be also causing an interlocking action and resisting the motion. The definition of friction is the force that resists the relative motion between two objects or materials. Of importance at this point is to understand that the direction of the force resists the motion. So if the motion is from left to right, as in this example, and let's make that the floor, which is static. Let's make this the block, and let's assume that the block is being pushed from left to right. The force it experiences as a result of the friction is opposing the motion, so it would be from right to left. Now, to quantify the extent of this friction, we use the term friction coefficient, okay, which is shown here as mu. Now, mu is simply a ratio between that frictional force that you get, that resisting force, upon the normal force, as we call it, the force pressing the two surfaces together. So if we go back to that block example, here's the floor and here's a block that is resting on the floor. Now, between the block and the floor is most definitely a compressive force, felt by the floor as a force downwards, felt by the block as a force upwards. So if we zoom in and we look at this little gap between the two, and we insert in there that compressive force and its effect on the block. Now remember, these arrows that we show here are all the effects felt by the block. So this is in essence a free body diagram of the block. The block feels the upward arrow from the normal force. It itself experiences weight, gravitational pull of the earth, which is experienced as a downward pull. And then we're applying a force in this example from right to left. So motion is going to occur from right to left. Now here is the frictional force. Now the frictional force is very simple to understand. It always opposes motion. So this block, which is moving from right to left, is being resisted, or the force of friction is resisting its motion. So if motion is this way, it experiences the frictional force in the opposite direction, and it experiences it at the surface of rubbing. Remember, there isn't actually a gap here. Now mu is the ratio between the frictional force and the normal force. Now newtons at the top and newtons at the bottom gives us ultimately a unitless ratio, and that is called the coefficient of friction. Now, for convenience, let's group mu nf as a product on the one side of the equal sign, and let's leave friction force on the other side. What that means to us is that frictional force is in fact always equal to the product of mu and normal force. So in most of the problems that we do, we will simply insert that as the frictional force. We won't use f. We'll always just use it as the product of mu nf. That saves a lot of time. Oh, and in this example, I've also crossed out the acceleration arrowhead, because in this example, as given here, there is no acceleration. We are moving at constant velocity, so there's no acceleration. Later on, we'll bring in acceleration, But for this example with constant velocity, these would be the only forces experienced by the block. 1, 2, 3, 4 forces, keeping the block in equilibrium whilst it is moving at constant velocity. Let's start with this little example. Once again, it's a block and it has weight of 200 newtons and it's moved by an inclined pulling force. The last example, the force was horizontal. In this case, it's inclined at 30 degrees to the horizontal, as shown here. And you are told to determine the horizontal component of the applied force, as well as a few other things. So let's start with that. So the horizontal component of the 50 Newton force would be the component running this way. Now, if you cast your minds back, we came up with a simple way of replacing a single force with two components. And the little system that we used was, we take the original force and we rotate it in our minds through the given angle. The given angle in this case is 30 degrees. So we take the 50 Newton force, we pivot it around there, and we end up with an imaginary arrow this way. That will be, as we call it, the cos component. So it will be original force 50 cos 30, and it will be to the right. And then by process of elimination, the other component, which in this case is most definitely upwards, would be 50 sine 30. So the answer to A is simply 50 cos 30. You can work it out and write down the answer. And the second one, the vertical component, is simply 50 sine 30. And that is upwards, and this is to the right. Next is to find the normal reaction N. We refer to that as NF normally. And then finally the coefficient of friction. So let's start with a free body diagram. There's our block hanging in space. And we then must insert all the forces as experienced by the block, with single arrowheads as experienced by the block. Remember, that is the rule of free body diagrams. So we start off by showing which way motion is going to be. I use a double arrowhead with an M showing motion. So in our minds, we understand that this block is either moving from left to right or on the point of moving from left to right. And we start by inserting the components of the 50 Newton force. The 50 Newton force itself is gone and it's been replaced by the two components, as we said before. To the right, 50 cos 30, upwards 50 sine 30, experienced on the corner of that block. Next, we do the weight. Through the center of gravity of the block, straight down towards the center of the earth, is its weight of 200 newtons. Then, between the block and the surface is most definitely a compressive force, and that is felt by the block as an upward push, which we're going to refer to always as N subscript F, standing for normal force. Normal meaning perpendicular to. And then finally, opposite to motion, we insert our friction force. And as we said earlier, we're going to use that always as the product of mu and NF. And it is simple to understand the direction. It is opposite to the motion. If the block is going from left to right, mu NF will be from right to left. So we have 1, 2, 3, 4, 5 forces keeping this block in equilibrium. So if the block is in equilibrium, the sum of the vertical forces must add up to 0, or put another way, forces up are equal to forces down. So let's do it the latter way. Forces up, NF, as well as 50 sine 30, NF as well as 50 sine 30 are the only forces experienced in an upward direction by the block, and therefore they must be equal to the only other force experienced by the block in a vertical direction, which is 200 down, and from that you can solve for NF at 175 newtons. Then we do the same for horizontal forces, and there are only two. 50 cos 30 is to the right, and mu NF is to the left. So from that you can solve for mu, which comes out at 0.247, no units, remember it's a unitless ratio. That is the coefficient of friction for this block. Just to reinforce what we just did, let's do an almost identical one, except in this case the applied force is a push, not a pull, but the method is identical. We've got to find the horizontal component, the vertical component of the inclined force. So we can do that straight off. we take the 10 Newton force and we rotate it in our minds through the known angle, which is 25 degrees. So I'm going to take that force, and in my mind I'm going to rotate it until it is facing that way, horizontal from left to right. I would then have reached the cos component. 10 cos 25 right would be the answer to A. The answer to B would be 10 sine 25 downwards. Note that this force as drawn here can only have vertical component, which is downwards. It can only have horizontal component, which is rightwards. Next, we've got to find the normal reaction, which we refer to as NF, and finally the coefficient of friction, exactly like the previous one. So there's our free body diagram of the block. Our components, 10 sine 25 down, 10 cos 25 right, as we did moments ago. Then the 60 Newton force of weight through the center of gravity. NF, the normal force, which is between the surface and the block itself, perpendicular to it. And then lastly, if motion is from left to right, the resisting force of friction is from right to left, and as we've done before, it is the product of mu and NF. So once again, we sum vertical forces equal to 0, in other words, ups equal downs. We have up NF, and we have down two forces, 10 sine 25, there's that one, and 60, both down. From it we find NF at 64,23 newtons. Then we do sum of horizontals again, equal to 0, or alternatively, lefts equal rights. It means the same thing. So we have from right to left mu NF, and from left to right 10 cos 25. We solve for mu at 0,141, no units, a unitless ratio, the coefficient of friction. Next we must do angle of friction. Okay, first of all, let's have a look at what this vector is here. That is the resultant of friction force, which we normally refer to as mu NF, and normal force. So the resultant of those two is that single force out there. Then if we look at the angle between it and the normal force, we get this little angle over here, and that is referred to as angle of friction. Okay, and the bigger that angle, the more friction your two surfaces possess. Okay, so as this grows and this stays the same, so this flattens out and this angle becomes bigger. So it would appear as if there's a relationship between this angle and friction. The rougher the surfaces, the more grip there is, the bigger will be this angle. So it's just a very little used, very seldom used concept, a way of expressing the amount of friction. And it relates to mu, which we already understand. Remember, that was that unitless ratio that we dealt with before. The relationship between mu, the normal way of expressing the amount of friction, and this new concept of angle of friction is tan phi. Why is that? Because tan phi relates to those two vectors according to this little triangle. You can figure that part out. Now, straight after doing angle of friction, I want us to do angle of repose. And the reason is the two are often confused, even though they are two totally separate issues. So angle of repose is the angle at which a block will just stay on a slope. That is just before it starts to slide. If you increase this angle any more, the block will then slide freely down the slope. So repose suggests rest. So that block will stay at rest on this slope at this particular angle. If you increase that angle just a tiny bit, it will start to slide. The angle at which that happens is called the angle of repose. So let's look in more detail at the forces acting on this block as it is resting on the slope just at the point of sliding. Okay, let's start with motion. Motion is either about to happen or is already happening at constant velocity from right to left. In other words, down the slope. Gravity is pulling the block down the slope. And all the forces are identical whether you are on the point of sliding, so sliding is imminent, or you are alternatively sliding at constant velocity. If there is acceleration, it's another matter. So we are not going to have acceleration. because that would mean that we have gone too steep with this angle. So this block is either on the point of sliding or is sliding at constant velocity. Right, what are the forces acting on it? Well, through the center of gravity we have weight acting down towards the center of the Earth, but as we learnt a few lectures back, we can replace that single force of weight with two components, one downslope, which is always weight sine slope angle, and another force into the slope, which is weight cos slope angle. So that sorts out those two. And the reason for using those two components is it's going to be easy to sum with the other forces, which are all parallel or perpendicular to the slope. That's why we replaced weight with those two components. Next, there must be a normal force acting under the belly of the block, and that comes from the compression that occurs between the block and the slope. Definitely between the block and the slope there is compression because the two are being squeezed together. The block feels the arrowhead that way. And finally, the force of friction, which resists motion, we've learned that already, occurs at the surface of rubbing, and it is in the opposite direction to motion, and we like to put that in, remember, as the product of mu and nf. Let's start by summing the forces parallel to the slope. Okay, so we have W sine theta as a force parallel to and down the slope, and it's equal to the only other force that is parallel to the slope, which is mu nf. Let's call that equation 1. Next, let's sum the forces perpendicular to the slope, and there we have nf equal to W cos theta, equation 2. Then let's take equation 2 and put it into 1. So wherever we see an nf in equation 1, let's replace it with W cos theta. And that would give us the following. And then we can make mu the subject of the equation, and we end up with W sine theta over W cos theta. W's cancel, and you're left with tan theta. So that is the confusion between this and the angle of friction. The formulae look very similar, yet they are completely different. What is the use of all of this? Well, if you know the angle of repose, you effectively know the mu between those two particular materials that are rubbing against each other. So it's a very useful, practical way of determining the coefficient of friction between two materials, and you might then use that coefficient of friction in your design or other work that you need to do with that. So let's use what we've just learnt with number 16. In number 16, they tell us a 220 Newton block of metal just slides, that's important, just slides down a slope inclined at 27 degrees to the horizontal. Determine the coefficient of friction, and then determine the magnitude of the force parallel to the slope to pull the block up the slope. So first things first, we were told that the block slid at 27 degrees. And we've just learned that that was another way of determining mu. So mu is equal to tan 27, which is 0.509. That then is the coefficient of friction between those two materials, regardless of what you then do to the slope, the forces, etc. Next is to find the required force to slide that very same block up the very same slope with the same angle. Now that angle could well have changed, but in this example they kept the angle the same. But the difference is the block is not sliding down the slope as before under the influence of gravity. You are now applying a force and making it go up the slope. So motion is from left to right up the slope. So let's do the free body diagram as before. There's the applied force. Opposite to the applied force is the friction, which we know by now we use the product of coefficient and normal force. The normal force itself is that arrowhead from the compression arrowhead pair as felt by the block. So that compression between the block and the slope is felt by the block as a force NF that way. Then finally, the actual weight of the block acts towards the center of the earth, we know that, but we're going to replace it with a component downslope, which is always weight sine slope angle. And hand in hand with that is always the other one, which is the component into the slope, which is the very same weight, cos 27. So we have 1, 2, 3, 4, 5 forces keeping this block in equilibrium. Remember, it is equilibrium because it is moving with constant velocity up the slope. Let's sum the forces perpendicular to the slope, of which we have only 2 by the looks of it, NF and W cos 27. So out of that you can find NF at 196.02 newtons. You can then use that when you sum forces parallel to the slope, of which there are 3. P is up the slope, and then down the slope is W sine 27, as well as 0.509 NF. And instead of NF, you can put in the 196.02 you just worked out, and you can find that the force required to move this block up the slope is 199.65 newtons. Now try the tutorial on page 106 and do numbers 22, 23, 19 and 25.